This is a demonstration for ESE 5160 A12G, demonstrating the working of the port connector, which is a part of the sensing mechanism of the PCB that has been designed. So basically we were running out of GPIOs because of due to which we've added a port expander that can be seen over here to add these GPIOs. So I'll be going over the driver followed by the implementation. So this is a basic driver that has been written for the port expander. So like you can see, this is the initialization that has been taken from the data sheet. So it is basically connected to the GPIO-A port as inputs, and we setting the bits to 1 for an input mode, and passing the I2C address and the buffer for processing, for reading in the data, and the I2C data write data wait function with the appropriate timeout. We're enabling the internal pull-up registers for the buttons on the GPIO-A port. So I'll just show you how it has been connected. Uh, so it has been, so this is the port expander, and it's connected. It has two ports, GPA and GPB. We are connecting it particularly to GPA port number A0, 1, 2, and 3. So this is where our buttons are placed, and then it is interfaced over the SCL and STA line with the microcontroller over PA08 and PA09 respectively. So this is our read function where we'll be detecting the state if it goes high, if the button is pressed or no. So it will just read the current state of the GPIO-A pins, and this is the particularly the register address to read from, which has been given in the data sheet. It has been defined as a macro separately in the .h file, as you can see. So yeah, so I'll be reading the state of the button through this function, adding a small timeout, and then returning the state of the GPIO-A pins. Through this function, what I'm doing is particularly detecting which button was pressed, and using some bit manipulation logic, and basically checking and printing for each button, assuming like it has an active low configuration. So like we have 4 buttons. If you look at this expression, what we're particularly doing is it's shifting the value left of the SPI button. So it's like presumably a constant representing the bit position of the SPI button in the GPIO state variable. So it'll set the bit corresponding to SPI button 0, while all the other bits will remain 0. SPI button will be 1, others will be 0. So this performs like a bitwise AND operation between the GPIO state variable and the value obtained from the previous step. So this will isolate the bit representing the SPI button, and if the button is pressed, this bit will be 0, and if not pressed, it will be 1. So the NOT operator will negate this, and so basically if SPI button is pressed, the result will be true, which is 1, indicating that the button is pressed, and if not, it'll stay 0. So that is how it is being used in the driver. So this is an overview of the driver. Coming to the main.c, how I'm using it. So I have a dedicated function that has been written that will determine the state, and I'm also toggling the LED, which I'll show in the demonstration now, and a separate button that will toggle the LED. I have a separate task determined for it, like you can see over here, and passing the parameters accordingly. This is my main.c. So I'll show you the demonstration of it working. So these are the 4 GPIOs that I want to use. So the logic that I'm implementing is that once I press it, the LED will toggle. So that's how they're working. I'll be also demonstrating it through the CLI. So like you can see, CLI is open. I'll just reset it, and then say I press the first button, which happens to be the GPIO button. That's what I get, followed by say I press like a UART button. That's what I'll get. After that, I'll have the SPI button and the I2C button, and I can go in any order. It will just determine which button was pressed. So yeah, that's it. Thank you.